Hello, and welcome to the lecture on 1.8. Today we're going to talk about inequalities. Let's start with a definition. An inequality is a relationship between two algebraic expressions where one is greater than, less than, greater than or equal to, less than or equal to the other. The solution to the inequality is all of the values of the variable that make the inequality true. All right, let's do an example now. Suppose we have the inequality 3x plus 4 is less than or equal to 16. So now what we need to do is we need to find all the values that x can take for which the inequality holds true. So we're looking for when this expression is less than 16 for some value of x. So let's just start with a t-chart really quickly here, and we'll see what values x can take. Let's start with, say, 0. Okay, so if x is 0, the expression on the right would be 4. Is 4 less than or equal to 16? Yes, this is true. If x is, say, 2, plug in 2. We would have 6 plus 4 is 10. Is 10 less than or equal to 16? Yes, it's less than 16. So it fits this inequality. Also true. Try 4. So we plug in 4, we get 12. 12 plus 4 is 16, is equal to 16. So 16 is equal to 16. This still holds true because we have this is less than or equal to, and it is equal to. So it satisfies this inequality. This is also true. But we can see that 4 will be the last one that actually satisfies this. If we continue to make our x larger, say 5, then we'll see that it becomes false. So if we plug in 5, 3 times 5 is 15, and 15 plus 4 is 19. 19 is not less than or equal to 16. So this becomes false. So we have all these values that are true. Now we obviously can't do this forever, because literally it would take forever and we would still not finish. So instead what we're going to do is look for when it changes from true to false. Well, at 4, this is the largest value that this side can take while still being less than or equal to 16. So if we draw a number line here, you can say at 4, this will be the largest value that x can take, so that 3x plus 4 is less than or equal to 16. So let's plot 4. And then all values that are less than 4. All of these values are values that x can take and make this inequality true. Now, I do need to make a note here that we are plotting values between the integers. So even though over here I only plugged in integers, x can take any real number between the integers on this side. All right, the next thing that we're going to talk about is the rules for inequalities, what we can do with them. So here we have the rule, and we have the description. 1. A is less than or equal to b if and only if a plus c is less than or equal to b plus c. Adding the same number to both sides preserves the solution set. 2. A is less than or equal to b if and only if a minus c is less than or equal to b minus c. Subtracting the same number to both sides preserves the solution set. 3. If c is greater than 0, then a is less than or equal to b if and only if ca is less than or equal to cb. Multiplying a positive number to both sides preserves the solution set. if C is less than 0, then A is less than or equal to B if and only if CA is greater than or equal to CB. Multiplying a negative number to both sides reverses the inequality sign. If A is greater than 0 and B is greater than 0, then A is less than or equal to B if and only if 1 over A is greater than or equal to 1 over B. This property actually follows directly from property 3. If you multiply both sides by 1 over AB, then you'll get this exact property. You should try that. Taking the reciprocal of both sides reverses the inequality sign. 6. If A is less than or equal to B, and C is less than or equal to D, then A plus C is less than or equal to B plus D. The smaller expression in one inequality can be added to the smaller expression in another, so long as the larger sides are also added. This preserves the inequality. If A is less than or equal to B, and B is less than or equal to C, then A is less than or equal to C. Inequalities are transitive. On number 6, I want to make a note because this is sometimes confusing to students. We can add A to C because it's the smaller expression in both inequalities. Adding A to D and B to C will give us no relationship. We don't know which side will be bigger because we know B is bigger than A and C is less than or equal to D, but we don't know how much bigger or how much less than they are. Okay, now we're about ready to start solving linear inequalities. Definition. An inequality is linear if each term is a constant or a multiple of the first power of a variable. Let's do an example of these. So let's solve this inequality. Say we have 5x is greater than 7x minus 8. All right. We can go back to our rules to determine what we can and cannot do, but here we can subtract something from both sides or add something to both sides. So what I'm going to do is I'm going to subtract 5x from both sides to get all of my x's on one side. Now I have 0 is greater than 2x minus 8. Now I want to get x alone, so I'm going to add my 8 to the other side. So we add 8 here, add 8 here, and this side will cancel and we'll be left with, I'm going to flip my inequality, 2x is less than 8. Note that all I did, if I add 8 to this side, 8 is greater than 2x is the same thing as saying 2x is less than 8. So I just changed the sides of my inequality and flipped it. So 2x goes here, but it still is less than 8. Then I divide by 2, both sides. Same thing as multiplying by 1/2, and that would be rule 3. We can multiply by a number as long as it's positive. As long as it's positive, the sign will not change. So we're multiplying by 1/2 on both sides, and we get x is less than 4. Now to graph this, all we have to do is find 4. Now we have that it's less than 4, not less than or equal to. So we have an open hole here, or if you prefer, you can have a parenthesis. And all of these values. This is how it would look if you used a parenthesis instead of an open circle. Another example. 4x minus 12 is greater than or equal to 7x minus 15. Okay. You should probably pause the video and try to solve this one on your own. What I'm going to do first is get all my x's on one side and all of my constants on the other. So I'm going to add 15 to both sides and subtract 4x from both sides. So I'm doing two steps in one. Here, 4x minus 4x, so I have no x's on the left anymore. And then negative 12 plus 15 is 3. And then I have 7x minus 4x is 3x. And negative 15 plus 15 is 0. So then I multiply by 1/3 on both sides, or divide by 3, same thing. And we get that x is less than or equal to 1. Again, I flipped my inequality. I flipped the sides of the inequality as well. So again, 3 divided by 3 being greater than or equal to 3x over 3 is the same thing as 3x over 3 is less than or equal to 3 over 3. Or, in other words, x is less than or equal to 1 is the same thing as saying 1 is greater than or equal to x. You don't have to have your variable on the right if you don't want to. It's just common. And some people like it that way. Now we're talking about x being less than or equal to 1. So any number on the number line that's less than or equal to 1 will fall within our solution set. So we have all of these numbers. We have a closed circle because we're less than or equal to. If you were to do parentheses or brackets, because we're less than or equal to, you would have a bracket and a line like this. I want you to try one. Solve the inequality 4x plus 5 is greater than or equal to 13. The next thing that I want to talk about is going to be solving nonlinear inequalities. So start off by recalling a couple of things. And I know this particular recall is going to be pretty straightforward, pretty standard, that we all know it. The product or quotient of any number of even negative values or factors is positive. The product or quotient of any odd number of negative values or factors is negative. An example of this, I know we probably don't need one, I just want to go over it anyway, but if we have -3 times -4 times 5, we have an even number of negatives, so this is going to give us a positive because the negatives will cancel out. So we end up with a positive 60. Now for the other one, if we had -2 times 3 times -4 times -5, now we have an odd number of negatives. So we're going to have a negative value after we multiply all these out. And this ends up being -120. But this plays a very key role when solving nonlinear inequalities. Solve the quadratic inequality. So when we solve a quadratic inequality, what we want to do is start off by solving it as if it was an equation and not an inequality. So we're going to do everything that we've done prior. Get everything on one side, let the other side be 0. So let's subtract over our 7x and our 18 to the other side. And we end up with x squared minus 7x minus 18 is less than or equal to 0. Now what we want to do is factor. So we look for two numbers that multiply to -18 and add to -7. And this will be -9 and 2. Now again, note, like always, if you have a 1 as your coefficient of your x squared term, we can go straight to the factorization. X minus 9 times x plus 2 is less than or equal to 0. Okay, now this is where it differs. If it was an equation and not an inequality, we would use the zero product property, and we would say that x is equal to 9 and x is equal to -2. But because we have an inequality, there are going to be other numbers that make this true because we can be less than 0. Okay, so instead, what we have to do now is sort of look at a table here. So what I'm going to do is I'm going to look for where these two things are equal to 0, as if we were using the zero product property. So on the number line, these two are going to be 0, or this side of the equation will be equal to 0 when x is equal to 9 or x is equal to -2. So if we plot those, 9 and -2, then we can see that our number line is going to be broken up into 3 sections. All right. Now, the reason that we look for where these are equal to 0 is because this will actually graph out a curve. And when that curve dips below 0, that's when this inequality will be true. It has to reach 0 before it can go from positive to negative. Or it has to reach 0 before it can go from negative to positive. So what we do is we break up this into 3 sections. Right? Now I'm going to write this here as x plus 2 and x minus 9. And we have 3 sections. So if x is less than -2, so if we're in this section over here, we have to look to see whether we're going to have a positive or a negative value in this table. Now, if x is less than -2, then what we're saying is that x could be -3 or -4. You can pick a value that's within this region and use it as a test point. So let's pick -3 because -3 is less than -2, but it's close enough and small enough that we can use it very nicely. So if x is -3, we get a -3 plus 2. Well, -3 plus 2 is negative. So we get a negative value. Whenever x is to the left of -2, x plus 2 will give us a negative value, corresponding to this x plus 2. Now, similarly, if x is less than -2, subtracting 9 will keep the sign. So if we had -3 and we plug that in, we would have -3 minus 9, which is -12. So we have a negative value here as well. So again, if x is left of -2, then x minus 9 is going to be negative. But that product is going to be positive because we have an even number of negative numbers being multiplied together. We have x plus 2 times x minus 9, and if we're to the left of -2, both of these values are going to be negative. So the product is positive. Then we move on to the next one. Now, I want to note before we move on why we're doing this. And I can note very easily using this as an example. So look over here. We have the x minus 9 and the x plus 2 is less than or equal to 0. So we're looking at this product, but the product is positive when x is to the left of -2. So if x is to the left of -2, then this product is positive, and if this product is positive, is it going to be less than or equal to 0? Does it make this inequality true? Well, we know that we'll have a positive number in this region. So on this region, the x values do not satisfy the inequality because we would have a positive number, and a positive number is not less than or equal to 0. Okay, so let's move on to the next region. Suppose we're between -2 and 9. So now we're in this region on the number line. Now, if we plug in a number, we can use 0 as a test point. If we plug in 0, we would get 0 plus 2. Now that's a positive number. So we have a positive number here. Use 0 again. 0 minus 9 is negative. -9 specifically. So we get a negative here. So one of the terms is positive, one of the terms is negative. So we have that their product is going to be negative. Now we look back at our inequality and we see that x plus 2 times x minus 9, x plus 2 times x minus 9 is going to be negative, which is less than 0. So it does satisfy. So we could say that this region does not satisfy. This region does satisfy. And let's move on to the third region, where x is greater than 9. So if x is greater than 9, let's say 10. 10 plus 2 is positive, so we get a positive value here. 10 minus 9 is also positive, so we get another positive value here. Positive times a positive is positive. Now, if we have a positive number, we can see that our positive number is not going to be less than 0. It's not going to be less than or equal to 0 because we have a positive value. That means that on this region, when x is greater than 9, this inequality is not true. So it does not satisfy the inequality. So the only region in which this inequality is true is the region between -2 and 9. So our solution set is -2 to 9. Now we use brackets because it's less than or equal to 0. Now there are times where we won't use a bracket even though we're less than or equal to, and we'll see one in an example coming up, and I'll explain it when we get there. But when we have, for this particular example, we use brackets because we have less than or equal to 0. When x is equal to 9, we would have 0 times 11, which is equal to 0 and thus satisfies the inequality. When x is equal to -2, we would have -11 times 0, which is still equal to 0 and thus satisfies the inequality. So -2 and 9 need to be included in the solution set, hence the brackets. Okay. And we can see on our graph that we would have either brackets here or a closed circle or a bracket, and this will be the graph of our solution. For our next example, this one gets a bit tricky. So I want us to be very careful when we do this one. X minus 1 squared and x plus 3 divided by x plus 1 is going to be less than or equal to 0. Now I want you to be careful with this one. This one's already factored, so we're already within the multiplication and division step here. So all we really need to do is draw our chart. This chart's going to be a bit longer. We have x minus 1, quantity squared, x plus 3, and x plus 1. We also need to know for which regions we're going to test points. So, we look at what makes each of these equal to 0. X plus 3 is 0 when x is -3. X plus 1 is 0 when we have a -1 here. And x minus 1 is 0 when we reach 1. So we have 4 regions now. We're going to break this chart up into 4 regions corresponding to each of these regions. Now here, this is when x is less than -3. This is between -3 and -1. This is between -1 and 1. And this is when x is greater than 1. Okay, so these are the regions they're checking. So, first things first, when x is less than -3, we have to check what happens to each of these factors. Let's start with x minus 1 quantity squared. Now you'll notice something with this particular factor, I want to see if you notice it. I'll reference it at the end. But if x is less than -3, we can plug in a test point, say -4. So we plug in -4, and we have -4 minus 1, which is -5. -5 squared is positive 25. So this is positive. Now, if x is less than -3 for this one, say again -4, we use test point, x equals -4 will give us a negative value. -4 plus 3 is, of course, -1. And if we use a -4 here, we have -4 plus 1 is -3, which is also negative. And here, x minus 1 squared times x plus 3 divided by x plus 1. So this one is going to be a positive number times a negative number divided by a negative number. So the positive number times the negative number gives us a negative number, and then we divide by a negative number, and a negative number divided by a negative number is positive. So this will be a positive value. And then we can check to see if it satisfies this inequality. If we have a positive number, is a positive number less than or equal to 0? And that answer is clearly no. So we mark this off as it does not satisfy our inequality, and then check the next region. -3 is less than x is less than -1. So a number between -3 and -1, we can use a test point of -2. Plug in a -2, we get -2 minus 1 is -3, and -3 squared is +9. So we have a positive value here. Okay. Keeping with this, if we use -2, we have a -2 plus 3, we have a positive value. -2 plus 1 is negative. And then we look at this quotient. Positive times a positive divided by a negative gives us a negative value. Is a negative number less than or equal to 0? Yes. So on this region, because the quotient is negative, it will satisfy this equation. Thus, all of the values between -1 and -3 satisfy this inequality. Now let's use the next test point between -1 and 1. And that's an easy one. We just use 0. 0 minus 1 is -1. -1 squared is positive. So we get a positive value here. 0 plus 3 is positive. Positive value here. 0 plus 1 is positive. So we get a positive value. Positive times a positive divided by a positive is positive. On this region, between -1 and 1, we have a positive quotient. This quotient is positive, which means that this quotient is positive because it's the same thing. So between -1 and 1, we have a positive is less than or equal to 0, which does not satisfy the inequality. So we go back here and we say, no, this does not satisfy. Then we move on to the last region, when x is greater than 1. Now, if x is greater than 1, we have, say, a test point of 2. 2 minus 1 is 1. 1 squared is 1. We have a positive here. Plug in a 2 here. 2 plus 3 is 5. We have a positive value. Plug in a 2 here. We have 2 plus 1 is 3. That's positive. And then we have a positive times a positive divided by a positive is positive. So we go back to our quotient and say, is a positive number less than or equal to 0? No. So it does not satisfy on this region. Okay. So now we need to come up with our solution set. And be careful here. There is a lot of nuances when you're dealing with quotients. Okay. So first things first. We know that if it's less than -3, it's not a part of the solution set. If we're between -1 and 1, it's not a part of the solution set. And if we're greater than 1, we're not a part of the solution set. So we know between -3 and -1 we are. So we have -3 and -1. Now we need to determine whether we have brackets or parentheses around our interval. Well, -3, we are less than or equal to 0, but we need to make sure that -3 satisfies this inequality. So if we plug in -3, we get a positive number here times 0 divided by a -2. So something times 0 divided by -2 gives us 0. So we do include -3. So we have a bracket. Now with -1, it's a little bit trickier. You have to be careful with this one. Up to this point, it would be intuitive to say that it's included. But for this particular quotient, it's not. If we plug in -1, we get a -2 squared, so 4 times 2 divided by 0. Now, since we can't divide by 0, we have to exclude -1 from the solution set. Even though we have a less than or equal to, even though that the equal to sign is here, we exclude -1 because it makes the denominator 0. It's not even in the domain. Okay. And there's one other value that makes this true. You have to be careful here too. See if you can find it. Here, we know that we are not a part of the solution set between -1 and 1, and we're not a part of the solution set if we're between 1 and infinity. But at 1, we are a part of the solution set. If we plug in 1, just 1, you get 0 times 4 divided by 2. 0 times 4 is 0, 0 divided by 2 is 0, so 0 is equal to 0. So it does satisfy. So this solution set is actually kind of an unusual one, where we have an interval union with just a number 1 here. Because we're equal to, if we plug in 1, we get equal to 0. Now these curly braces means that we're going to list out values, and the value starts and ends with 1. It's only a list of one number, which is the number 1. I want you to try one. Solve the inequality. X minus 2 times x plus 4 is less than 0. Okay. Be careful, we have a less than here, not a less than or equal to. All right, so the next thing that I want to talk about is inequalities that involve absolute values. So let's start with the properties. Basically, what the absolute value is when it comes to inequalities. So 1, if the absolute value of x is less than c, then -c is less than x, which is less than c. I'll explain these when I get through these properties, but for right now, I'm just going to kind of go through each one and say what they mean on the right. So absolute value of x being less than or equal to c means that -c is less than or equal to x, which is less than or equal to c. If the absolute value of x is greater than c, then we say that either x is less than -c or x is greater than c. And if the absolute value of x is greater than or equal to c, we have the same thing, but with equality underneath. So it looks like this. So first, let's recall what absolute value actually is. The absolute value of a number a is the distance a has from 0. So if we say that the absolute value of a is equal to 3, what we're saying is that the distance a has from 0 is 3 units. So a is 3 units away from 0. But that's equality. What if we have inequality instead? So if we're saying that the absolute value of x is less than c, what we're saying is that the distance that x has from 0 is less than c. X is closer to 0 than c units. Another way of saying this is that x is within c units of 0. And on a number line, what this looks like is if we have 0 here, say that this is C, and this is negative C, noting that this is C units, and this is C units. So we have C units to the left and C units to the right of 0. That means that x must be within this range. It has to be somewhere in here. It could be here, it could be here, it could be here, but it's within C units of 0. Now, algebraically, what that says is that x is less than C, because it's to the left of C, and x is greater than negative C, because it's to the right of negative C. So x is between negative C and C, so x has to be greater than negative C and less than C. Similarly, absolute value of x being greater than C, what this means is that the distance x has from 0 is at least C units, or x is C units or farther from 0. So what that means is, on a graph, suppose we have 0 here, this is C, and this is negative C, then x is farther away from 0 than C units. Since this is C units away, x is farther away. So it has to be greater than C. So x is going to be within this region out here. Also including C because we have equal to. Similarly, this is C units to the left of 0. So x has to be farther away from 0 than C units, so x can also be to the left of negative C, also including negative C, specifically because we have equal to C. So it can be exactly C units away or more. Now what this leads to is that x is less than or equal to negative C. As we can see here, we're to the left of negative C. Or x is greater than or equal to C, because we're to the right of C here. Let's do an example of these. Find the solution. Absolute value of 2x minus 4 is less than 12. Okay, so I want you to think about what this means on a number line. So again, we have 0, here's 12, and here's negative 12. Now, 12 units from C is this distance here. Shouldn't do that in red. 12 units from C is this distance here. We're saying that this value, whatever this is, 2x minus 4, will turn out to be some number. That number, whatever this is, has to be less than negative 12. It has to be within 12 units of C. And that's 12 units to the right, and then we have 12 units to the left, which looks like this. So we know that our 2x minus 4 is going to be within this range, somewhere here. So we can say that negative 12 is less than 2x minus 4, which is less than 12, because this is the range that 2x minus 4 must fall into. It's between 12 and negative 12. And then we just solve for x like we normally would. Add 4, because I want to get rid of this 4. Now when I add 4, I have to add 4 to all sides of this inequality. It's a compound inequality where we have this is greater than something and also less than something else. So we have to add, when we add a value, we add it to all of these, all three regions here. We get negative 8 is less than 2x, which is less than 16. And then we want to divide by 2. And we get our solution set, which is negative 4 is less than x is less than 8. Here's our solution set. We also write this as an interval, negative 4 to 8. We use parentheses because we don't have an equal to here. We have strictly less than signs. So the interval for which this inequality is true is here. Now what this means is that x can take any value on this interval and it will make this inequality hold true. Do another example here. Suppose we have the inequality 3x plus 1 is greater than or equal to 4. So now we need to solve this inequality. It's a similar situation. Let's draw a number line. Put a 0 here. 4 and negative 4. So what we're saying here is that whatever 3x plus 1, whatever number 3x plus 1 turns out to be, that number needs to be farther away from 0 than 4. So it's going to be in this range out here. This range indicates that it's farther away from 0 than 4 units. And this range also indicates that these values are farther away from 0 than 4 units. Remembering that 4 units, it takes 4 units to get from 0 to negative 4. So when we look at this, we're saying that 3x plus 1 is less than or equal to negative 4 from this region, or 3x plus 1 is greater than or equal to 4. And that comes from this region out here. Then we just solve for x in both of these inequalities, and you do the same steps, so I usually do them together. In this case, I'm subtracting 1 from each side. And we get 3x is less than or equal to negative 5, and 3x is greater than or equal to 3. Divide by 3. And I get that x is less than or equal to negative 5/3, and x is greater than or equal to 1. Now, when we write this as an interval, we need to be careful. We go all the way down to negative infinity because x is being less than or equal to negative 5/3. Numbers down to negative infinity are less than or equal to negative 5/3. So we go negative infinity, always a parenthesis on an infinity, comma, and the maximum value that x can be on this inequality is negative 5/3. So we have negative 5/3, and since we have less than or equal to, since the equal to is there, we use a bracket. Now we have to union with these values. So we're saying x is either in this interval or the interval I'm writing right now. Now we use a bracket because it's greater than or equal to. The equal to is within the inequality here, so we use 1 here. And values up to infinity are greater than 1. And again, a parenthesis because we have an infinity here. So what this is saying is that x is either in this interval or this interval. Now if I want to graph this, we do negative 5/3 and 1. And we graph like this. Similarly up here, if we wanted to graph, we would have negative 4 to 8. And we have parentheses, or we have either parentheses or open circles because we do not include the endpoints for this particular interval. Now let's talk about another example, but in the context of modeling. Ando Onaka and the Wequayan pirates can steal a Republic freighter and its cargo, or a Hutt freighter and its cargo. The Republic freighter is worth 150,000 credits, and its cargo can be sold for 1,000 credits per crate. The Hutt freighter can be sold for 100,000 credits, and its cargo can be sold for 2,000 credits per crate. How many crates must be aboard the ship for the theft of the Hutt freighter to be more profitable? We assume that the number of crates is equal on both the Republic and the Hutt freighter.
I smell profit.
Okay, we employ similar process. We start with looking for the variable. What are we looking for in this problem? We employ a similar process to solving this problem to when we used equations instead of inequalities. So, what is the variable? What are we looking to find? How many crates must be aboard the ships for the theft of the hut freighter to be more profitable? X is going to be the number of crates aboard the freighter. This is the number of crates aboard each freighter. All right, now we need to set up our inequality here. If the pirates steal the Republic ship, they get 150,000 credits immediately for selling the freighter, and then its cargo can be sold for 1,000 credits per crate. Now, the number of crates is X, so 1,000 times X will be the amount of credits that they get from selling the crates. So we'll have 150,000 plus 1,000 X. This is going to be the total number of credits that they receive from stealing the Republic freighter. But we're looking for what value of X makes the hut freighter more profitable. And the hut freighter has a similar expression. They can sell the hut freighter for 100,000 credits, and its cargo can be sold for 2,000 credits per crate. So we get 100,000 credits plus 2,000 X. Again, this is the number of credits that they would get from selling just the freighter, and then 2,000 credits per crate times the number of crates will be the number of credits that they get from selling all of the cargo. Now let's look for X. Solving for X, we subtract the 100,000. Subtract 100,000 from each side, and we have 50,000 left over here, plus 1,000x is less than 2,000x. Now I want to get all my x's on the same side, so I'm going to subtract my 1,000x over. And then we're left with 50,000 on the left is less than 1,000x. 2,000x minus 1,000x is 1,000x. Then we just divide by 1,000. And we're left with x must be greater than 50. If there are more than 50 crates on each freighter, then it's more profitable to steal the hut freighter. All right, I want you to try one now. The gravitational pull of the Death Star on a Nebulon B frigate is given by the equation F equals 4 million divided by d squared, where d is the distance in kilometers from the center mass of the Death Star to the center mass of the frigate. For what distances will the gravitational pull exerted by the Death Star on the frigate be between 0.0004 newtons and 0.01 newtons? Now, I'm going to give you a hint here because I realize this is kind of complicated. We're looking for something that looks like this. F measures the force, so we have that the force is going to be between 0.0004 newtons and 0.01 newtons. So this is what we're looking for, or this is the equation that we have set up. And we want to solve for d. You're looking for what distances? You're looking for the distance, and d is the distance within the problem. So you're looking to solve for d in this problem. Okay, that's going to be it for today. I will see you all in the next lecture.